Welcome to the Elon Musk Signal channel. On June 25th, GOES-U, final satellite in the GOES-R series, was successfully launched aboard SpaceX's Falcon Heavy rocket. Earlier forecasts had indicated unfavorable launch conditions, but luckily, the weather unexpectedly improved to a 70% chance. Successful launch. At 5:26 p.m. Eastern Time, 21:26 UTC, the powerful rocket soared into the sky, roaring thunderously and drawing enthusiastic cheers from the gathered crowd, witnessing this moment. So what breakthrough features does GOES-U have? Let's join the journey to explore GOES-U in this video. This marked the 10th launch of the Falcon Heavy rocket. Falcon Heavy, a heavy-lift launch vehicle composed of 3 modified first-stage boosters clustered together from SpaceX's Falcon 9 rocket, provided a completely different experience compared to previous launches of the GOES-U's sibling satellites, which were launched using United Launch Alliance's Atlas V rockets, type of rocket without reusable capabilities. However, in today's launch, the central core booster failed to land safely due to needing too much fuel for achieving the required thrust, leaving insufficient fuel for a controlled Earth return. According to the plan, if all goes well, Falcon Heavy's upper stage will place GOES-U into a geostationary transfer orbit, about 35,785 kilometers, 22,236 miles from Earth, approximately 4.5 hours after launch. At that point, the satellite will be renamed GOES-19. The mission control team will conduct comprehensive checks on GOES-19 and its instruments for a period of time. Once completed, GOES-19 will replace the GOES-16 satellite, launched in November 2016, and currently operational in the GOES East position within the GOES satellite system. Naming conventions for the GOES satellites can indeed be quite intricate, you agree? Launching the Falcon Heavy rocket into orbit demands immense power. In this GOES-U mission launch, the rocket will utilize 3 entirely new boosters. The main core of the rocket, designated BTAM-87, will be fortified with additional fuel. The distinctive feature lies in the 2 side boosters, BTAM-72 and BTAM-86. They are tasked with landing back at LZ-1 and LZ-2 after completing their mission. Upon recovery, both boosters can potentially be reused in the future, either as side boosters for Falcon Heavy or converted into single-core Falcon 9 rockets. At 50 minutes before launch, the first stage booster began filling with RP-1, a refined form of kerosene. Approximately 5 minutes later, the process of loading liquid oxygen into the first stage booster commenced. When fully loaded, the total mass of liquid oxygen and RP-1 in the first stage booster, including both the main core and side boosters, reached approximately 287,000 kilograms and 123,000 kilograms, respectively. 5 minutes before liftoff, the second stage booster started receiving RP-1, followed by liquid oxygen pumped in about 17 minutes later. With just 7 minutes to launch, the 27 Merlin 1D engines were chilled prior to ignition. Just before T1 minute, the onboard computer of the Falcon Heavy initiated the countdown sequence as the rocket transitioned to startup mode, followed by the pressurization of the fuel tank. Seconds before liftoff, the 27 engines on both the main core and side boosters began igniting sequentially with the support of triethyl aluminum, triethyl borane ignition mixture. As all engines reached maximum thrust, the rocket checked operational status. All parameters were nominal, allowing the colossal 5.1 million pounds of thrust to lift the rocket off Launch Complex 39A. Less than a minute after liftoff, Falcon Heavy reached max Q, the point of maximum aerodynamic pressure during its ascent. All 27 engines continued operating until about 2.5 minutes into the flight, at which point both side boosters simultaneously shut down and separated from the main core just seconds apart. They performed a flip maneuver forward before executing a second burn, known as boost back burn. This deceleration burn adjusted the trajectory of BTAM-72 and BTAM-86 to facilitate their return to LZ-1 and LZ-2 for landing. Approximately 3.5 minutes after liftoff, a series of events unfolded in succession. First, the 9 engines on the central core booster shut down before it separated from the second stage booster, a few seconds later. Next, the Merlin vacuum engine on the second stage booster initiated in a process known as the first second stage engine start, SES-1. Immediately after, 2 payload-fairing halves, which protected NOAA's GOES-U satellite, were no longer needed and jettisoned from the rocket, falling back to Earth for recovery. Meanwhile, over 7 minutes after liftoff, 2 side boosters began their low-thrust burns as they re-entered Earth's atmosphere once again. This prepared them for their final burns, known as landing burns, for each booster. This ignition sequence helped slow down the rockets until they gently and successfully touched down at LZ-1 and LZ-2, separated by a few seconds, completing their mission approximately 8.5 minutes after leaving the launch pad several miles away. While the side booster's landing process unfolded, the second stage booster completed its first burn, followed by the first stage engine cutoff, SECO-1. Next came the activation of the second stage engine, propelling the second stage and the GOES-U satellite into geostationary transfer orbit. The satellite's final orbit will be circular, positioned 22,236 miles above the equator. Scheduled to officially begin its service as GOES East around April 2025, it will be located at 75.2 degrees west longitude. GOES-19, also known as GOES-U before becoming operational, will monitor a significant portion of the Western Hemisphere with its 5 advanced scientific instruments. One of GOES-19's critical roles is monitoring and studying space weather, enabled by the Compact Coronagraph 1 (CCOR-1) instrument developed by the Naval Research Laboratory. Today's launch is part of a 5-decade-long cooperative relationship between NOAA and NASA, involving the operation of over 60 satellites, providing data for weather forecasting, climate research, and hurricane prediction. The current operational lifespan of the GOES-R series extends into the 2030s. This mission is succeeded by the Extended Geostationary Observation Satellite System, the first satellite expected to launch in 2032. Geostationary Operational Environmental Satellites. GOES witnessed the debut of GOES-R in 2016 aboard an Atlas V rocket. While NASA and NOAA jointly manage a fleet of weather satellites, the 4 latest satellites, including GOES-U, offer triple the observation channels, 4 times better resolution, and 5 times faster scanning capabilities compared to their predecessors. This information is crucial for near real-time weather forecasting, particularly valuable during severe weather events like hurricanes. These satellites operate 24/7 with minimal interruption times. Monitoring weather now resembles fluid watching rather than watching films, flipping through pages or cartoons. For intense storm activities, whether in the face of chaotic boundaries accompanied by thunderstorms or hurricanes, human intuition can read the movement of that fluid and integrate information with other data collected from ground-based observation devices and satellite devices that do not provide images but can provide information on high-altitude temperatures. Thanks to GOES-U, we can forecast hurricanes more accurately, monitor the formation and movement of tropical storms, as well as monitor other dangerous weather phenomena such as tornadoes, floods, and wildfires. GOES-U is not just a weather satellite, but also a tool to protect humans and property from natural disaster. And those are the noteworthy highlights from today's broadcast. Please leave your comments on this episode and stay tuned for more exciting events in upcoming episodes. Thank you for watching. Don't forget to subscribe and turn on notifications to catch more interesting videos on the Elon Musk Signal channel. Goodbye, and see you again.